So I'm Dylan, this is Andrea, and today we'd like to talk to you guys about physical human-robot interaction and how the robot should respond to it. So consider some sort of personal, assistive, or household robot that is accomplishing some task for the person. In our simple example, the robot is moving a cup from some start location to a goal. And now imagine that there's a person, here Ellis, in close proximity to the robot. Ellis is happy with where the robot is carrying that cup, the task that the robot's doing, but he's unhappy with how the robot is getting there, specifically the trajectory that the robot follows. In order to fix what the robot does, he can physically interact with the robot, push, pull, twist, apply some sort of forces and torques, trying to get the robot to behave in a manner that he wants. We're going to refer to this as physical human-robot interaction, or pHRI. The major question that we want to address in this talk is, how should the robot respond to this pHRI? Now, of course, we're not the first to ask this question. Within the controls literature, there are a variety of different techniques that all address this fundamental issue. To briefly summarize them, probably the first and maybe the most basic would be to treat the human as a disturbance who should be rejected and ignored. So now, whenever the human interacts and applies forces to the robot remains rigid, and the human can't change its position. The robot strictly follows some sort of fixed trajectory, and the human can never affect how the robot accomplishes this task. So if you look here, the robot's going to follow the y trajectory no matter what the human does. A second approach, and in many ways an opposite approach, is to treat the human as an expert who should always be trusted and followed. In this case, at every time step where the human interacts with the robot stops moving and enters a gravity compensation mode. This makes it very easy for the human to backdrive the robot along their desired trajectory, which you can see here in red. However, once the human lets go of the robot again jumps back to its original trajectory, just like we saw in the last slide. I think a third approach, and the most common approach to physical human-robot interaction within the literature today, is impedance control. Now, this approach combines aspects of both of the two approaches that we've just talked about. The robot here is always trying to follow some sort of fixed desired trajectory, and when the human interacts with the robot responds by rendering an impedance. For instance, it can behave like a spring. Now, this makes it very easy for the human to deform the robot's position through physical interaction, sort of like you see here with the gray line. Unlike the disturbance rejection scheme, now the human can change how the robot accomplishes the task. And unlike the gravity compensation scheme, the human gets force feedback from the robot, letting them know what the robot wants to do. Even with impedance control, this very common scheme, something appears to be missing. So let's look at this video of a person interacting with a robot that's using impedance control. Here, Ellis wants the robot to move this cup closer to the table. And so, with impedance control, it's very easy for him to push on the robot, and it responds compliantly. What happens when he lets go? The robot jumps back again to its original trajectory. And so he has to keep pushing on this robot repetitively in order to make it go closer to the table. One thing that we noticed by looking at each of these different strategies is that in all of them, the robot resumes its original behavior as soon as the human stops interacting. And while this might make a lot of sense from a controls perspective, we don't think it captures the whole problem. In fact, in this talk, we argue that you should take a step back and reason about why the human is interacting with this robot in the first place. So again, returning to this example, the reason that Ellis is interacting with this robot is because it's carrying the cup of coffee too far above the table. It's too high in the air. And he's interacting to move that closer to the ground. But why is the robot carrying that cup of coffee too high? Well, that's because this behavior is optimal with respect to some objective function. The robot thinks it's doing the task in the best possible way, and robots move according to their objectives. But if he's interacting with the robot and trying to correct its behavior, clearly the robot is doing something wrong. And so it has the wrong objective function. So in this work, what we're arguing is that instead of the robot returning back to its original behavior as soon as the human lets go, like we talked about in the previous approaches, instead, the robot should, 1, reason about why the human is interacting, and then 2, update its objective function according to this interaction. Once the robot updates its objective, it can then replan the rest of the trajectory, as shown here in orange, in a way that's better in accordance with the human's preferences. So to summarize, we don't want robots that are stubbornly trying to do the same task throughout. Instead, we want robots that respond, learn, and update their objective based on physical human-robot interaction. And that right there is our insight for this work. Physical interactions are intentional and therefore informative. We can get information about the way that the robot should be performing this task based on physical interactions. And so with that in mind, actually the approaches that I described previously, while they might make a lot of sense, are in some ways heuristics. They don't really get at the fundamental problem that we think exists within pHRI. In fact, we can leverage our insight that we just talked about in order to formulate pHRI as a dynamical system where the robot is unsure about the correct objective function and the human provides information about it. So let's talk about this system. First, the robot has a state x, and it takes actions UR. The human takes actions UH, and the robot transitions according to its dynamics, which depend on both the human and the robot actions. So both of us can affect how the robot moves. Finally, the robot has some sort of reward function. Importantly, both the robot and the human share this reward function. It's the same for both parties. The reward function R considers the robot state, the robot action, the human action, and theta, a reward parameter. In this talk, we're going to split the reward function into 2 different parts. First, there's a task-related reward. Similar to previous work on inverse reinforcement learning, we are going to set up this task-related reward as a linear combination of features, where theta determines the relative weight or importance of these features. Theta is a parameter vector that captures the robot's true objective. Now, if the robot always acted optimally with respect to theta, the human would never need to interact. The robot would be doing the task just the way the human wants it, and the human will be happy with how it behaves. This would minimize the human's effort. So clearly, we want the robot to optimize with respect to theta. But importantly, the robot doesn't know theta, this true objective function. Only the human knows theta. One sort of fundamental idea within our framework, though, is that the human's actions actually provide evidence about this hidden parameter theta. We can construct an observation model which connects theta to human actions simply by assuming that the human is rational, that they are approximately trying to maximize the robot's objective function. And that's it. That is how we would formalize reacting to pHRI as a dynamical system. And you'll notice that it's actually a partially observable Markov decision process, or a POMDP. Now, the reason that we're introducing this as a POMDP is not because we're going to, in the rest of the talk, try to solve it using POMDP solvers. Unfortunately, that's right now too hard to do in real time for online implementation. Instead, we think that this formalization is important because it provides a very clear problem statement. Instead of relying on the heuristics, which I previously described, we now know exactly what the optimal solution should be. And we can come up with different approximation techniques which provide good and efficient ways for the robot to learn in real time. So now I'll turn it over to Andrea, who can tell you guys about what we did in this paper to solve the problem.
So the core question here is, how can we make robots learn online from a human interaction? So to answer this question, we broke this down into 3 major approximations from the full formalism that we just talked about. We separated estimation from control, we separated planning from control, and finally, we used a map estimate instead of tracking the full belief. So let's dig a little bit deeper into what each of these approximations mean and how we actually got here. So in the first approximation, we simply separated estimating the true reward parameter theta from solving for the optimal control policy. So at every time step, the robot is simply updating its belief and then replanning with this new belief. However, if you look at how the robot actually has to compute this optimal control, it has to compute the Q-value function for like every single theta that it actually is keeping track of. And we unfortunately can't actually compute a full policy in real time. So instead, what we're going to do is we're going to reason in the plan space instead of directly in the action space. and move into our second approximation. In our second approximation, we're going to separate planning from control and shift reasoning from control space into trajectory space. This means that now we're going to have the robot plan a trajectory by maximizing this cumulative reward, and then tracking this trajectory by using an impedance controller. This impedance controller was chosen specifically for two reasons. First, people can physically modify the state of the robot, and second, the robot is compliant to ensure human safety. If we look back at the estimation of our reward parameter theta, again, this estimation step still depends on the Q value. So here too, we're going to shift reasoning from action space into trajectory space. So now we're saying, what is the probability of a human's preferred trajectory given the robot's current trajectory and our reward parameter theta? This only requires us to compute the cumulative reward across the trajectory, which is a lot more feasible in real time. However, the question becomes, the person is giving you an interaction force, not a full trajectory. So what is this psi-h, this human's preferred trajectory? The way that we're going to reason about this is we're going to take a reasonable guess by propagating the human's interaction force throughout the robot's planned trajectory. So here, in this white line, you see the robot's original planned trajectory. The human's going to apply an interaction force UH, and then we're going to smoothly deform the robot's original trajectory in the direction of the force to get the human's preferred trajectory psi-h. This allows us to get a simplified observation model across trajectories, which only requires us to evaluate cumulative reward values along a trajectory, which is much simpler than before. Finally, if you notice in the estimation step, our theta is continuous, it's high dimensional, and our observation model is still not Gaussian. So what we're going to do is we're going to instead start to reason about the maximum a posterior estimate and replan at every single time step, then tracking the full belief. In this paper, we find that the map estimate of the reward parameter theta under a second-order Taylor series expansion about the robot's objective psi r with a Gaussian prior actually ends up being online gradient descent. And this is a very elegant approximation to the POM-DP and leads to an intuitive update rule that the robot will use at every time step to update its knowledge of theta in the direction of the feature difference between the original trajectory it had and the human's preferred trajectory. In learning from demonstration literature, this is analogous to online max margin planning and coactive learning. But here we're going to be using this update rule specifically for learning within a task, while in prior work it has been used for learning between two tasks. Putting all these things together, we now have a full algorithm for online learning from pHRI. Here you see a robot has planned a trajectory from start to goal around these two obstacles, O1 and O2. A human's going to apply an interaction force UH at some time t. The robot's going to deform its trajectory in the direction of that force, compute the difference in features between its original trajectory, the human's induced trajectory, update its objective relative to that, and now the robot can replan a more optimal trajectory relative to the human's interaction force that consistently moves away from all the obstacles in the environment. We now took this algorithm and we evaluated it in a user study and compared it to a baseline where we were not actually actively reasoning about the robot's objective. So we had 3 household manipulation tasks and 10 total human participants. The robot would move from a start to a goal position with an initially incorrect objective. The 3 tasks included a task that was moving a cup from the shelf down to a table, but the robot would be tilting the cup initially. Another one was the robot moving on top of a table, and the human wanted to move closer. And the last one had a robot moving over a laptop, which the person did not prefer. We had 2 major hypotheses from this experimental setup. Our first hypothesis was that learning will significantly decrease interaction time, effort, and total trajectory cost. And our second hypothesis was more related to the subjective measures, that participants will better know if the robot understood their preferences, feel less interaction effort, perceive the robot as more predictable, and believe the robot's more collaborative when it is actively learning. So here's an example from our first task and our experimental results. People had to physically intervene while the robot was moving to teach it to keep the cup upright. On the right, you see our learning condition. On the left, you see our baseline of just the impedance control method that's not updating its objective.
Yeah, if I could jump in. For the impedance controller, like we talked about earlier, the robot is always trying to follow the same desired trajectory. And so the human has to keep pushing the robot back to how they want it to behave. Whereas with learning, it's actually understanding what the human wants, and then it can replan the rest of the trajectory in according to the human's desires.
In the second task, we see a similar sort of behavior. In this task, people were told to teach the robot to move closer to the table throughout, One interaction in the learning condition results in the robot continuously moving closer to the table, while in impedance they have to continuously interact. Again, this is because the robot is actively reasoning about the features that it knows about and what the human might care about.
Yeah, I don't think we need to rush here.
Finally, we have the last task, where participants were told to teach the robot to not move over the laptop. So here, once again, notice the interaction paradigm. Human pushes on the arm to move it away from the from the laptop. All of these examples that we're showing you right now are running the same exact algorithm consistently.
Yeah, and so really all that changes between them is the different features that we provide the robot with. Like we just said, the underlying process is the exact same. So you could imagine how we could do this in different scenarios just by giving the robot the features that are important to the task.
So we analyzed the results from these experimental tasks. We split it into objective and subjective metrics. In the objective metrics, we looked at the average cost across tasks and found that across all 3 of our experimental tasks, when the robot was actively learning, compared to the impedance, it decreased the average cost significantly. We also found, if you look here at a sample participants' data, that if the blue trajectory is the desired trajectory that the human would like the robot to perform, it takes about 1 interaction for the person to converge to the correct optimal trajectory in the orange learning condition, while with the gray, the human has to keep pushing down, as you can see in the deformed trajectories. We also looked at the total human effort and the interaction time and found significant effects across all tasks, where learning significantly decreased total human effort and interaction time for all 3 tasks compared to impedance. We also asked all participants at the end of their interaction to fill out a 7-point Likert scale survey about how they felt interacting with this robot. Here are some of the sample questions that they were asked. And we found, after performing a one-way repeated measures ANOVA, that for understanding, for effort, and for collaboration, participants significantly felt that the robot was better when it was actively learning. Ultimately, in this work, we find 4 major contributions. First, we find that human forces can be used and leveraged as observations about the robot's true objective. We also find that limited information, just the torques that people apply on the robot, can be used to update the high-level model that the robot has about what it's actually doing. We also find that online max margin planning and coactive learning are approximations to this full POMDP that we talked about earlier. And finally, we find that robot objective functions can be learned in real time simply from physical human-robot interactions while the task is unfolding. So ultimately, in this work, we propose that robots should not treat the forces that people apply on them simply as disturbances and reject them. Rather, they're intentional and informative. And robots are capable of updating their understanding of their task and learning simply from human physical interactions. Thank you very much.
Thanks, everyone.
All right, we have plenty of time for questions, so if anybody has any questions to ask, please step up to the microphone.
Thanks. How did you choose the features?
Do you want to take this one?
So the features right now were hand-coded for the specific task that we wanted to test, but they can be extended for whatever particular task that you would like. In this paper, we don't focus on feature selection explicitly, but you can imagine that you can construct these in any sort of way.
What kind of features did you actually have then here?
Yeah, so I think one of the important aspects of these features is that they're very intuitive to the human. So for example, one of the features was distance of the robot's end effector to the table. So how far is the cup above the table? Another one was the orientation of the cup. Was it straight upright or was it at an angle? So there are things that both the human and the robot can understand in like a very intuitive way.
And it's important that the human and the robot share an understanding of what the feature space is so that they can both understand each other and interpret the right signals.
Right. Thanks.
So when you showed the last video where the robot is trying to avoid the laptop, the cup was actually not upright. So if the human wants to actually teach both, keep the cup upright and avoid, how would the algorithm react to more than one parameter to optimize for?
Yes, so right now there were 2 features that the robot was trying to understand. One was like a path length feature, and the other one was a task-specific feature. You can extend this to many different things where the person can incrementally provide corrections across many different features.
So yeah, what we're interested in maybe in ongoing work is understanding whether you should correct one feature at a time the human should only be able to change one of these very intuitive features, such as the orientation, the copy, the distance from the table, or whether you should just change them all at once based on the human's interaction. And this is definitely something that we've been thinking about, and we'd be interested in your thoughts as well.
So can this approach be generalized by using kind of virtual interactions, in the sense that instead of specifying a reward function, you can kind of like figure out the actions that you would make to fix the robot?
So you're talking about maybe computing the Q value, like maybe the optimal set of actions with respect to some reward function, or could you maybe
like for
elaborate a bit
example,
more?
like if the quadcopter is falling, you would like push it up.
Okay.
Or like in general, like could that be like a different way for specifying a reward function, instead of like specifying the reward function as like a virtual force and torque to fix the robot?
It might be problematic to reward the robot for receiving these forces and torques, because that will encourage the robot to actually perform poorly so that the human corrects it. Perhaps we should talk later so we can better understand exactly what your question is, unless.
Are you talking about like the way in which a person can give the preferences that it has to the robot, or is it that the robot should hallucinate sort of like what are the possible ways a person will correct me, and then from that I'm going to do that?
Yeah, exactly. Like
Right.
if the robot thinks that like the corrective force would be large, then that would be like a cost for the robot to minimize.
Right, so I think that's captured right now in the way that we've set up our reward function, where we have a portion that is related to the task and a portion that's related to the human effort. So in general, the robot is trying to trade off between these two and like minimize the human's effort, but maximize the task reward.
And the observation model sort of captures exactly what you're describing. We would expect the robot to push, the human to push the robot closer to the table if they wanted the robot to move closer to the table. So there's sort of like a causality or like a rationality that's built in right into the observation model.
So the robot has that intuition for what that mapping should look like from the observation model explicitly.
I see.
Thanks.
All right, let's thank the speakers one more time.